Recording has started. Please go ahead.
Okay, shall I start?
Yes.
Okay, a very good morning and a very good evening to all participants. And once again, thank you for joining today's session. This is session number 13, and we are in the second part of our entire discourse. This is on quantum computing. More specifically, we are discussing a few algorithms out over here. Last week we started this topic. We discussed what is meant by the Deutsch algorithm. We introduced the Deutsch algorithm as a special case of a Deutsch-Joseph algorithm. We had also shown the implementation of that in Qiskit. Okay, so let me quickly wrap it up one more time and then I will move forward in today's session. And today we are going to talk about what is meant by quantum oracle. Actually, this was supposed to be covered last week, but because of paucity of time, I shifted it to discuss in this week's session. So I will talk about quantum oracle, and then there are different two types of oracles which normally are used: the XOR oracle and the phase quantum oracle. I'll typically talk about both these two, and then we will also see how to construct the quantum oracle. Now, more specifically, the oracle is supposed to be a black box, right? Something like a black box wherein you give some input and it generates some output. The input is called as a query, and the output is typically something like a response. And only you know this information about how the responses are observed for some given inputs, and you really do not know what has gone into this particular black box, right? So that's how oracles are. So but what we will do is, when we talk about implementations for our understanding, we will try to build an oracle for a specific known function. So that's how we can test it out, right? So for example, we'll build it for a NOT gate, or we'll build it probably for a Hadamard gate, right? So we'll build an oracle which is supposed to be imitating the behavior of a Hadamard gate, right? So we will be discussing those aspects as well, and we will talk about how to run that on the IBM the Qiskit. Post that, Prakash will get into what is meant by the Grover's algorithm, a very, very interesting algorithm per se. Once again, this Grover's algorithm we are going to cover in two sessions. Today, Prakash will talk about what exactly is the core concept behind the Grover's algorithm. And next week, I'm going to take an IBM Qiskit implementation of this Grover's algorithm. Okay, so this is what we're going to cover today. So last time we spoke about the Deutsch algorithm, and it's essentially a implementation in a quantum phenomena. It's basically a quantum circuit, and what it takes is it takes the input, which is typically in the plus minus type of the domain, and converts that right into an output once again which is in the plus minus, and depending upon the nature of that particular black box, the oracle. Now what is this oracle? Now the oracle, especially for this Doshi algorithm, tries to measure, tries to identify, tries to find out if a particular function that gets implemented is a balanced function or a constant function. Now what do you mean by constant function? Irrespective of whatever might be the input, if the output is always the same, unchanged, it could be either a 0 or a 1, ket 0 or a ket 1, then we say the function is basically a constant function, right? Whereas if I have a scenario wherein for some given set of number of inputs, half of the times if I get the outputs as 0, half of the time if I get the outputs as 1, then I say the fact that the black box, the oracle, is balanced. So my Deutsch algorithm does not give you any output for some input, but it only tells you specifically if the particular function f of x, whatever it is a balanced function or a constant function. And how does it essentially do? It will take the inputs, right? And that inputs normally are given in the plus minus. So we, to do that, what we do is we use the Hadamard gates and then try to position the inputs from your 0 1 to the plus minus. That is what we essentially do, and then we force these inputs to go to a function. This is the black box, the oracle. And at the output we measure and then we identify whether from the MSB part, and we need to do is just only measure the most significant bit, and from the MSB part I can measure and then find out if that particular function f of x represented by that operator UF, whether it is balanced or constant, right? So once again, to do that sort of a measurement, which I have to do it in the 0 1 space, what I do is once again I use this Hadamard gate to do that appropriate transformation from the plus minus to the 0 1 state. So this is the overall uh, behavior, and this is how we can also implement the Deutsch algorithm in quantum circuits, right? So let me tell you a little more about this. All we are now doing is what? Determining whether a particular function is a constant function or a balanced function. And doing all that jugglery, just by measuring if the MSB is equal to 0 or 1, I can determine whether it is a constant function or a balanced function. Now remember, this is for a Deutsch algorithm. For an this is primarily for n equals to 1, and if at all I've got more number of bits for a general n bit case, then once again I measure the MSB, and if the MSB is equal to 1, I know the fact that the oracle is a non-constant, right? So which also means the fact that it does not necessarily say that it is going to be balanced, but I know the fact that okay, the oracle has a function implemented which is not a constant. Whereas if the MSB is equal to 0, for sure I know the fact that the oracle is a constant oracle. Okay, so that is typically the more general case, which is for Deutsch Joshua type of a implementation. So let us look at both these two. This is for the case of a constant equal to 0. The moment you talk about a constant equal to 0, we know the fact that from an implementation point of view, the oracle happens to be equal to identity. And if the oracle equals to a constant, I do not know, this part did not, one second. I do not know why it did not load. Okay, if the oracle is said to be mapped as a constant 1, this can be implemented using a C0 gate. Okay, so let me also quickly take you back to what we mean by all of this. And this is once again for the benefit of all those participants who missed out the last time. Remember, what we are trying to do is something like this. This is what we are trying to implement, right? So this is more or less the overall behavior of the UF, the way the UF works. So the UF function operates on ket x, ket y, and the way the UF functions is defined as follows. This ket x is retained as it is, and the ket y is operated with using the exclusive OR operator on the function f of x, right? So we now realize a y, which is the second operator, exclusive OR with whatever is the function definition f of x. So this is essentially the overall underlying way your oracle operates, right? And remember, if at all we talk about, let's say, a 2-bit case, right, to 2 qubits, right? If at all we operate on that case, then what we essentially can get is 4 different combinations of the way the functions can be. So the idea is I now need to guess what is the type of a function I need to implement once I know the inputs and once I know the outputs. It's something like this, that a function being implemented is like trying to identify the transfer function of a system. Given the outputs, given the inputs, and all possible states of the outputs and the inputs, is it possible for me to determine the transfer function of the system? That is exactly what we are trying to do. And depending upon the inputs and the outputs, and I can now plug in the criteria. For example, if the function is a constant 0, right? If it is a constant 0, I just apply this. Notice the fact that f of 0 will always be equal to 0. F of 1 will always be also equal to a 0. So the moment I plug in the values of a constant 0 into this definition, you will see the fact that this state operating on the input state are the same. So I can now say the fact that I need an identity to implement a constant 0. And similarly, if you plug in out over here for a constant 1, right? So wherever you have got f of 0, f of 1, you replace that with a 1 out over here, you will get a C naught gate, right? Technically speaking, you will get something like this. You have got UF, right, operating on, let's say, ket 0 and another ket 0. So that will be equal to, if you just work it out, this will work out to ket 0 and ket 1. Okay, so it will work out to ket 0, ket 1. So if you just work out all these four combinations here, you will see that the behavior is just nothing but a C naught gate. So what does it also mean? If at all you have got a constant 1, I can replace that constant 1 implementation using a C naught gate for my oracle. Or if at all I want to just check out for a behavior of constant 0, I can typically realize my oracle using the identity function. Okay, so that is exactly what we have discussed last time also, and we have written these two circuits. So that was for constant 0, this is for constant 1. So constant 1 I'm just replacing with a C naught gate. So what I will do is very quickly I'll show this implementation on Qiskit, and then we will move forward to the actual part of my lecture. So here is the IBMQ platform. I just logged in into that. So let me get on to the composer part. Okay, so this is what it was. So I'll just show you, this is for a constant 1. I will also show you, right, this is about constant. Okay, I think I can edit this only directly. Don't worry. Okay, so I'm just going out over here. I'll just replace this with the identity, correct? So I'll just bring in an identity here. Sorry, I need to cut this off. I just bring in an identity here and also an identity here. So this is the first part of the circuit wherein I take the inputs and then apply the Hadamard to bring it down to the plus minus space, and then I have got the identity. So this is my oracle, and this is the place where I do the measurements, phase number 3. And if you look at this, I can just run this and inspect this. You already have seen the output here come down to 0, 0. If I just run this, inspect this, I can typically go stage by stage, step by step. So I just start off with the inputs. So inputs are accepted, and that at that particular point of time, my input state is 0, 1 for my system, and then I move forward. I'm applying the Hadamard gate, and that will position all of that into uniform probability of 25%. And then I move forward one more time. I'm now applying the identity. This is my oracle. Because it is identity, it does not really cause any change to the probabilities. You see once again all these four values at 0.25%. I move forward, and then I bring it back to this space. And the moment I talk about bringing it back to the 0, 1 space where I wish to do the measurements, now you see the fact that it boils down to 0, 0 and 0, 1, whereas they are having some probability which is 50%. Right? I'm just working it on the quantum QSM simulator here itself. And then if I go further down, it will just collapse down to 0, 0. And what is this 0, 0 meaning? In this 0, 0, examine only the most significant bit, and that happens to be a 0, indicating the fact that this is a constant function. Right? Remember, this is not just the output of the system, but the output that is generated, where the most significant bit is an indicative of what type of my function I am using out over here. What is the type of a function used in the oracle? So the identity function out over here in the oracle is a classic implementation of any function f of x, which is said to be equal to 0, constant 0. Okay, so I will stop this here. And what I will do is I'll quickly edit this same thing here, and then I bring in a C naught. And the moment I bring in a C naught, that is supposed to be representing a constant 1. Okay, so where is my C naught? I can just bring in my C naught, and this is my C naught. I'll plug it out over here. So my C naught has come in, and the moment I just have my C naught, you just see the fact that the output has not once again changed much. you'll see the output is the same. So let me quickly go through each and every stage, and step by step I'll do one more time. Simulate this. So that is, after the inputs are taken, then I pass it on through a set of Hadamards. So this is 2 Hadamards. So I call this as H, right? Plus 2, right? H plus 2. The superfix is the plus 2, indicating the fact that there is a series of 2 Hadamards out there. And that is now my oracle, right? The oracle does this. It basically applies the C naught, and then it generates an output, and that output once again collapses to the state measurement, and the state measurement still once again happens to be 0 0, and the most significant bit 0, indicating the fact that it is a constant function. So which means what the output you see will be the same whether the function is a f of x equal to 0 or f of x equals to 1. So for any of a constant function which produces a constant value, either a 0 or a 1, the most significant bit will always be equal to 0. What about a function which is a balanced function? Right? What happens if the function is a balanced function? What happens if that is the case? Just hold on. After the session, I'm going to show that implementation as well. And in the case of a balanced function, you will see the fact that the most significant bit now will be equal to a 1, indicating the fact that it is a balanced function. Okay. So I'll just leave this screen as it is, and then let me go down to my presentations. Okay. It's not loading. I do not know why. Yeah. So with that, let us now understand what is meant by now the oracle. So we'll now look into oracle, and we'll look into a generalized approach of implementing an oracle. Correct? So we know how the Deutsch algorithm is all about. So we can just also use the general same strategy for implementing an oracle, and then also apply and then try to see if that also behavior is good for some known gates. For example, we can try it out and implement, let's say, a NOT gate, or we can just try it out and implement a Hadamard gate, or we can just try the same technique and then implement the so-called Deutsch algorithm. So we will see all the 3 cases. So before that, let us once again understand what is the overall philosophy of setting up this entire type of an implementation. Right? Remember, we are talking about a general function f of x. We do not know what exactly is gone inside of the function, an oracle, as a black box. We can generalize saying the fact that it is a function which is defined over n inputs and produces some m outputs. Right? N inputs and m outputs. And as we have spoken earlier, for a Deutsch problem, we have n equals to m equals to 1. So 1 input and 1 output. And notice the fact that if at all there is a classical implementation using some classical gates, n not equal to m is all fine. So you could have a gate which can take 3 inputs and then produces 1 output, or you can have a gate which has got 4 inputs and produces 2 outputs. All that is very much possible in the case of a classical logic. But the moment you talk about quantum implementations, we have an issue. If the value of n is not equal to m, then you have got a black box, a quantum circuit, where n is not equal to m, and that once again sort of has to be implemented with a n cross m square matrix. N cross m matrix, and that is not going to be a square matrix. And because it is not going to be a square matrix, it is not going to be unitary, it is not going to be reversible, and it does not really become a what you call a quantum gate. So the moment you have got a scenario where n is not equal to m, we need to do some small jugglery. So what is the jugglery we do? We try to implement a box adding some additional bits at the inputs and outputs. For example, I've got n inputs and m outputs. I will now realize a box, a black box, which has got n plus m inputs and similarly n plus m outputs. And the moment I do that, then I have got a black box wherein I'll have n plus m inputs and n plus m outputs, the same number. So the internally this can be defined by a n plus m cross n plus m matrix. So the matrix now would be a square matrix, right? So what I need to do is what I just add up these additional gates and then force it to become a unitary and reversible type of an implementation. So what does this basically mean? So I'm going to add n plus m, or I'm going to add m inputs. The so-called a number of output lines, I'm going to bring it down into the input lines. Similarly, the so-called number of input lines, I'm going to carry them also onto the output state. And the inputs will be enforced onto the n lines, and the outputs will be grabbed onto the m lines. Okay, so I just do this small jugglery so as to create a quantum circuit which will be an n cross m circuit. So this is exactly what I mean to say. So I've got n inputs and m outputs. We now create a complete input basis vector which is xn ym. Remember, these y's are what? The so-called output bits, m output bits. I combine both of them together and then create a enlarged vector, right? Notice the fact that the MSB is denoted by the inputs and the LSB, which are M, are denoted by YM. So these are the least significant bits. So just once again, there is a different type of a notation given in other books. So just to remove that confusion, I'm specifically saying the fact that these will be the MSB bits. So here these XN values are identified as a query, that is input to the oracle, and the observation is typically done on the output side for yn. And from the input, whatever are the y lines, m input lines, these are called as the auxiliary or additional added qubits. Okay, so what we can do is something like this. We can implement these quantum oracles, and let us now understand what these quantum oracles are typically supposed to be giving to us, right? We have got two types of oracles, as I would say. Now these oracles are called as the XOR oracle and the phase inversion oracle. So we have got both these two type of oracles which are there. We will try to see the behavior of each one of them, right? Once again, remember, how does this oracle work? If at all I have got any input, right, the output will be y XOR with f of x. You're getting the point. So y XOR with f of x. That is basically the definition of how the oracle essentially works. And in our case now, what is my output? My output will be xn as it is, and the ym will be modified like this. So it will become y XOR with f of x, whatever is the function that is getting actually implemented, right? So remember, this is your classical bitwise XOR operation, and this entire thing is now represented in this manner. Okay, so this is an enlarged representation of what we discussed earlier on. So here you talk about xn, n bits, ym, m bits, and the function which is operating on this input basis vector will produce an output basis vector, and those will be xn and y m bits, but y is not as it is, but y is operated by this fx. And now what is the overall size? So we are talking in terms of the behavior which is in the C2 raised to the power of n plus some space, right? So the space is now an enlarged space. So okay, so here is the overall behavior. So this is my XOR oracle. My XOR oracle has got n plus m qubits as an input, and basically it has got n plus m qubits as an output. So internally, from a matrix representation, this would be n plus m cross n plus m. So I can now define it in this particular manner. So UF is my black box. I've got the query lines, and these query lines are my n input lines, and I add up these m output lines, so that now at the input side I've got n plus m. Similarly, at the output also I will have the m actual output lines, and then I'm now adding up these n input lines from the query coming out over here as it is. So if at all you look at this, the query, the input is given on the most significant bits, right? And the result is observed on the least significant bits. Okay, so this is what it is. So this is where I observe the result. Now there are some books which have different type of a notation. So even our book is also going to mention both these two with a small word of caution. And some of the books and some of the notations will just flip this role of MSB and LSB, but we are going to follow this notation, the upper notation as is mentioned in our quiz kit also. So we are just going to follow this IBM's quiz kit implementation notation so that there is no confusion. So this is the overall block of my oracle. Okay, so let us understand the behavior of this. So here is a small example where I am considering n equals to 3 and m equals to 2, and I'll assume the fact that the function that is implementing is f of x equal to some value, and for some very specific input x equals to 3, let us assume that the function gives me a value equal to 3. So let us assume this, and I need to sort of implement this, or I'll just check out the behavior of this, right? So what we now need to do is like this. In this particular function, the MSB bits will be f of 3, f3, right? f3 will be 0, 1, 1 in binary, and the least significant bits, m bits, will be equal to 2. So the input vector will be 0, 1, 1, 0, 0. So it will be a 5 qubit input, and similarly you are going to get a 5 qubit output given by the oracle. So how does the oracle work on this? It's an XOR oracle. So I have UF working on 3, 0, 3 bits of making up 3, 2 bits making up 0. And what happens is the internal operation going something like this. The 3 bits of 3 will be as it is. The 2 bits of 0 will be operated by the function, right? 0 exclusive or f of 3. Remember f of 3, because the input is 3, it will be f of 3. And I know the fact that f of 3 is given to me to be equal to 3. That is what I know, because remember, from an oracle I do not know how it is built, but I know the outcome for a given input, right? So I know the behavior. So using that, what I do is I plug that in here. So this becomes 0 exclusive or with 3. And if at all you just convert that, put them into binary form, 0 is 0, 0, 3 becomes 1, 1. Do a bit by bit exclusive or, you get this as 1, 1. And obviously now the result will be a 5 qubit basis state. So that will be 0, 1, 1, 1, 1. So this 0, 1, 1 is coming from the input, and 1, 1 is the actual output that is now generated on the two output lines. Remember, the output lines are two output lines. But now I'm actually operating over an enlarged space. I'm considering now 5 qubits which are required out over here. And if at all you look at the state space, this will be 2 raised to the power of 5 different states. Okay, so this is just to give you an idea as to how we use the XOR oracle, how the XOR oracle behaves on some. This is a partial information which I know. Remember, I really do not know what is the value of the function when x equals to 1. I do not know, because that has not been given to me. It could be anything. Okay. So the second type of gate is called as a quantum phase oracle gate. Right? What is this phase oracle gate? I have an oracle which does not really manipulate the bit values, excepting for the fact that it changes the phase of the input basis vector. So my fx is a function which primarily changes the phase of the input function. So that is what is called as a phase oracle. And obviously, because it only takes the input as it is, changes the phase, and then produces the same number of output bits, the oracle will always be an n cross n type of a oracle. So how is that function defined? So you have got uf, that is the function, and working on the input, which is x bits of the input, and it produces the same output x, but with this additional function, which is 1 minus 1 raised to the power of f of x. So what is that f of x? F of x is the implementation of that oracle. Okay, so this f of x as an implementation of an oracle works on that minus 1, and that particular minus 1 is the fellow which is responsible for producing the so-called phase shift. Okay, and if that particular f of x, that function, remember for a value of x, if it is working out to be even, obviously minus 1 raised to the power of any even power would be equal to 1, so that the output is the same as the input. Whereas if this f of x is equal to odd, minus 1 raised to the power of any odd value would be equal to minus 1. And that minus 1 is now interpreted as a phase shift of phi. So that is why this operator produces a phase shift of phi depending upon how the function is set up. If the function is an even function, then the output is same as the input. If the function is an odd function, then the output is phase shifted by phi. So such a oracle is said to be the phase quantum oracle. Okay, so this is a small verification of the same thing out over here. So let me not just get into that, but technically, if at all you just look at any two basis vectors A, B, then you typically identify their inner products, and then operating on the phase oracle, you just put up the phase out over here in both the cases. So for A as well as B, you just plug in the phases and you get the inner products. And once again, what it tells you is that the phase quantum oracle retains the inner product of the basis vector, right? So it is the only trying to change the phases of the basis vector, and it still produces the phases not at any arbitrary phases, but it produces the phase shifts in such a fact that they are still orthonormal. So with this, let us now get on to the interesting aspect of how to construct a quantum gate. Okay, so what we will do is we will look into defining a quantum gate. For that, we have a oracle. So let us first look at a generalized approach to constructing this particular oracle. Then we will look at a Qiskit implementation. So from what we have learned so far, if at all I have any basis vector to be represented, the simplest representation is in the form of a column. It contains essentially a column of all zeros excepting for one, right? 1 1, and that particular one denotes what exactly is the position of the basis vector, right? If it is a second basis vector, obviously now you'll have 0 1 2, so this point will be equal to 1. If it's the first basis vector, it would have been 0 1 0 0. We just know about this representation. So basically we have got a 4-dimensional space or C4 space with two bits, and I can just represent that in the form of a column vector, right? So what I will have to do is, given this sort of a representation, anytime I want to operate on this, I have to implement the operator as a 4 cross 4 matrix. That becomes my quantum gate, right? And that particular 4 cross 4 operator, when it works on this, it will obviously have an impact only at the row where a 1 is there, because all the rows where zeros are there, anyway it would not be generating any output. So the outputs will be caused only because of the operations of this column vector on the corresponding row vector out over here, right? So what does this mean? So this gives us some sort of an idea to work in the backward direction. I can do some re-engineering. So what is my idea? My idea is, given the behavior of the inputs and the outputs, is it possible for me to determine what is this 4 cross 4 matrix? So I want to estimate what is this 4 cross 4 matrix going to be, so as to represent the behavior as per this particular basis vectors for inputs and outputs. So that is basically what is our objective. Now what we will do is, we will just attempt this by working out on some known gates, and these known gates are maybe your inverter, right, or maybe the Hadamard gate, and so on and so forth. We will just try to use these known gates just to understand and reiterate the process which we are going to follow here. Okay, so let me move a little forward. So what is the general approach? The general approach is, I have to now create an n cross n matrix, right? So n cross n matrix, and I need to estimate what will be the values of this n cross n matrix. Okay, so I can typically say something like this. I will define this sort of an operator. The operator is, let's say, Braje U ket I, right? And what is this? I'm now creating the so-called quantum gate U. What is that quantum gate U? That so-called black box. So I'm assuming that the black box will operate on these specific values of J's and I, and these J's and I typically will be used to identify which row, which column are being targeted. So I would like to find out what is the behavior of that function for that specific targeted values of J and I, the position in that n cross n matrix. This is exactly what I'm trying to do. So what I need to do, I have to go through all the rows and all the columns, right? So for that, I just put up this sort of a sigma notation when I say J goes from 0 through n minus 1, I goes from 0 through n minus 1. So I can run through all the rows and all the columns. Remember, the columns and rows are numbered 0 through n minus 1. Right, so this is how I typically do this sort of an estimation of what will probably go into the quantum gate. Right, now this is pretty very important. This parameter is just nothing but a mechanism. Remember, which you have seen, this is a scenario where we try to identify the projection. So it will tell me what type of contribution this ket I has on ket J, right? So that is something which I'm going to use constantly here. So let us use this fundamental rule, and using this fundamental rule, we'll try to implement a few quantum gates. We'll try to implement a quantum gate which is already known to us, and then indeed validate the fact that yes, this way when I implement, I'm getting a C naught, and I know the fact that the C naught matrix is also this. So this is basically for cross verification. So here I'm trying to implement a 1-bit NOT gate, right? A 1-bit NOT gate. So this 1-bit NOT gate, not a C NOT gate, I'm sorry, it's a 1-bit NOT gate. We know the fact that the 1-bit NOT gate is actually defined by this. The U naught operating on ket 0 will produce ket 1. U naught operating on ket 1 will produce a ket 0. So this is the fundamental behavior, right? So what I will do is, remember, I will now plug in for a scenario where n equals to 2. There are typically two states with one qubit, right? Ket 0, ket 1. These are the two states. And what I will have is, I will have once again the two basis vectors, ket 0, ket 1. And I'll just plug in those values here. So it is a very simple jugglery which I'm doing. And what I'm doing is, I'm just applying the same thing. Let us see what it goes through. So J goes from 0 to 2 minus 1. Remember, that was n minus 1. Similarly, I goes from 0 to 2 minus 1. So initially it starts off with J equals to 0. That's 0. U naught coming up as it is. I equals to 0. That is the initial state. So I'll have 0. And so J and I once again become equal to 0, 0. So this will be the term that corresponds to the initial value of J equals to 0 and I equals to 0. So next time, because of the sigma, I still will remain equal to 0. J goes to 1. So that is represented here. So J is 1, U naught, 0, 1, 0. So this is for the third term where I is equal to 1 and J equal to 0. And this is the case where I equals to 1 and J is also equal to 1. Right? So these are the four different cases or expansions because of these operations. And U naught working on ket 0 is equal to ket 1. Similarly, U naught working on ket 1 is equal to ket 0. So I just plug in those values here. Nothing great. And then we are using these fundamental properties of this bras and kets, which we have studied. And this entire thing collapses. For example, this goes to a 0. This also becomes equal to 0. Out over here, this part becomes to a 1. This part also becomes to a 1. So it will just boil down to, right, 1, ket 1 and bra 0, ket 0 and bra 1, right? And notice the same thing which I expand it and then transform it into the column form and the row form, right? the kets are always the column form, bras are always the row form. If I just put them out over here and then do that multiplication, I will get these matrices added upon them, I will get this final resultant. So this is a matrix representation of whatever is a so-called NOT gate, which I realized using this mechanism, this fundamental mechanism. And we know this is just nothing but once again the same matrix representation what we have studied earlier also. Right? So this is indicating the fact that this strategy is definitely consistent. On similar lines, I'll not spend more time here. This is how I can also construct a 1-bit Hadamard gate. And for a Hadamard gate, we know this is how the function behaves. It takes Hadamard 0, converts that into +1, Hadamard 1 converts into -1. And that same thing is now what is represented here also. Just the same logic, right? Sorry. Right, so I'm just running through this and then putting up all the 4 combinations. These are the 4 combinations, and for each of these operator, h of 0 or h of 1, I just use this rule, plug in the values, and then you juggle around with the terms, and this is what I get, a matrix representation. And this is once again the same known matrix representation for the Hadamard gate. So which also I mean to say the fact that this is a consistent representation in terms of the behavior of any oracle. So which means what, if at all I know this output, this is what the output, right, and the input. If at all I just know the output and the input representations, I can construct this known matrix for the oracle. Okay. So what we will do is, very quickly, I will try to construct the matrix for the XOR oracle for the Deutsch algorithm. Remember, this is what we have seen. And I'm taking a very specific case for FB implementation. Remember, when we spoke earlier on, there are 4 different approaches, 4 different types of implementations, or 4 different type of functions are possible if at all you have got 2 inputs and 2 outputs, right? 2 inputs and 2 outputs are 4 different functions. So these are the first implementation of function A is a scenario where for a 0 it gives a 0, for a 1 it gives a 0. The second type of a function could be called as a function B, which behaves in such a manner that for a 0 it gives a 0, for a 1 it gives a 1. Right? So these are the 4 different types of implementations possible. So what we will do is, let us implement for FB. This is my FB. So I've just taken up this. This is also given in the book as an example. So for the case of FB, I know the fact that FB operating on 0 will give me 0, FB operating on 1 will give me 1. Right? So I can plug that in and then see the oracle transformations on the basis vectors. So when I do the oracle transformations on the basis vector, UAF operating on 0, 0 will be once again the same as per the definition 0. This one is 0, x is 0, and y would be what? Y exclusive or with the function. So I'll just plug that in out over here, and when I know the fact that f of 0 is equal to 0, that comes in here and it reduces down to 0, 0. And similarly, if I repeat it for everything, these are the outputs. And closely, if you observe, if you just observe this closely, what is typically happening? I now have got an XOR, right, which tries to give me a different type of a behavior. Okay, so if the input out over here is a 1, if this value is a 1, see the fact that the output will be flipped. Can you see the output is flipped? So which also means the fact that by just looking at this, I can now get a clue to the fact that, okay, this is good for a C0 type of a representation. Whereas if the input is a 0, the output is remaining unchanged. Okay, so this is exactly what I can deduce. Now, technically speaking, I have to derive the entire 4 cross 4 matrix, because we are talking about this entire the 4 inputs and the 4 outputs which will make up out over here. So it will be a 4 cross 4 matrix. So I'll have to work out with all the 16 possible cases. But what I will do is, I'll just have a shortcut mechanism wherein I don't have to really bother about the 0 cases. So I'll only bother about the 1 cases. So what are those 1 cases? So out of those 16 combinations, there are only 4 terms, 4 combinations which are the non-zero cases. So I'll just operate on those non-zero cases. The non-zero cases are these 1 values. and this will be for these 4 cases what you have seen here. These are the 4 cases. So I'll plug those same values now. So I know this fact, this is value is known. So I'll operate that on ket zeros and ket ones. And if I do that, I typically see the fact that the behavior can be interpreted with respect to these variations and the input variations. The input variations and the output variations, if at all I combine, I can get the representation to indicate whether this is going to be implemented using an identity function or a NOT function or a CNOT function or a Hadamard function or any other known functions. Remember, when we want to implement the oracle, we try to implement the oracle using a whole bunch of known functions. So here it is, the same thing expanding out over here and then juggling around with the terms. This gives me this sort of a matrix, and this matrix is a C-NOT gate, right? So basically, what it means is the Deutsch algorithm can also be implemented for the function type FB. Remember, this for FB. And that can be done using the C-NOT gate. On similar lines, you can try it for FC also, right? The best part about FA, B, C, D is, if you remember, FA and FD give you a constant outputs, whereas FC and FB typically gives you a balanced outputs, right? So that is the reason we have chosen FB. You can also similarly try it for FC. You'll get onto a similar lines. C-NOT can be used out there as well. So my quantum gate construction typically looks like this. It's once again the same circuit, excepting for the fact that out over here, I will now plug in a C-NOT gate. The C-NOT gate will be not the earlier type of a C-NOT gate where we had the control bit and data bit, right? It's now going to be flipped, and the moment I measure that, I will see the fact that the output will be equal to 1, indicating the fact that this is for a balanced quantum oracle. So what I will do is I will quickly take 2 more minutes and then demonstrate that. The program is already there, so I don't have to write it. So I have this as a balanced. Yeah, it's fine. So this is what it is. Okay, I put up once again, this is the part 1. This is my oracle. The oracle is now implemented as the C-NOT gate, and this is the place where I take the measurements. And now remember the fact that you require these Hadamards here. So this is 2 Hadamards, so represented as H plus star 2. So indicating the fact that this is application of 2 Hadamards on the 2 input states, and this is my 1 Hadamard wherein I am trying to do the measurement, and the measurements are done in the 0-1 space. So to transform from plus minus to 0-1, I use this Hadamard here. Okay, so let me quickly take you through stepping mode. And if you look at this, this is my first instruction which I'm getting executed. So the output state is 0-1. Okay, that is the input that is getting actually presented, and now I take it down to the Hadamard stage. Now you will see the probability will be equal across all the 4 state values. You can also see this in the Q sphere, and clicking this one more time, I take it through the oracle. The oracle just does the, maybe just only the probability is still once again remember the same, and then I move it further down to the Hadamard state, which is now grabbing the outputs, and now you see the fact that you just see the 2 possible output basis states as either 1-0 or 1-1 with equal probability of 0.5, and the moment I do a measurement, it will collapse down to 1 value. Yeah, it will collapse down to output equal to 1-0. Now what is this 1-0 meaning? Remember, this is not the output. You just have to examine the most significant bit 1. And the moment you look at the most significant bit 1, it is an indicator to the fact that this particular function that is implemented as part of your oracle is a balanced function. Remember, if the most significant bit were a 0, it is a constant function, constant 0 or constant 1. Here, the moment you talk about observing the MSB equal to 1, then you identify the fact that this is a balanced function. Okay, so if I'm just running on the simulator, that's why you are seeing this as 1 0. If you actually run it onto the machine, probably you'll see it as 1 0, and also a small uh, probability coming up here also for 1 1. That is because of the small error which happens when you have the actual implementations of your CNOT gate running onto the physical device. Okay, so what we have seen is we have had the so-called Oracle implementation for a constant 0, constant 1, and also for a balanced function. Okay, and we have also seen a generalized approach to build or construct any particular Oracle gate. We are going to use this technique or this funda in subsequent algorithms, especially when we come down to the Grover's algorithm and other algorithms. Subsequent week, I am also going to use the same background. Okay, so that completes my part of the session. Prakash?
Yeah. Can you hear me?
Yeah, I can hear you, Prakash. Okay, can you take
What
over from here? I'm going to stop
Yeah,
the
I can.
slide share. Yeah.
Yeah, you stop the slide share, and what I do is, where am I? Okay. So what I'm going to do is,
One second. Where is? How do I stop the slide share?
no, you just share. In the share, you click on the share. Yeah, I can share now.
Yeah.
I will
Okay.
share.
I'm stop sharing. Okay. Fine. Go ahead.
So let me share on share screen, and hopefully, so yeah. Can you hear me?
Yes, Prakash. I can hear you. I can see you also.
Loading the share. Okay.
Thank you.
So what I will do is I'll just go. We had done all this. What you had done. Yes, and growers. Oh, okay. I'll come to the growers algorithm. So what I'm going to do is we have around half an hour, I believe, and I will try to cover as much as I can, and then we'll move on to the next week after that. So we are talking about growers algorithm, the complexity associated with computation for that, the searching process in database with n entries, Grover's algorithm using qubits, and generation of Grover's algorithm. And probably implementation we'll skip, which will go to the next week. And that's what I'm going to do. So I'll quickly go through the algorithm. So first thing, Grover's algorithm is a search algorithm. You represent either you have a database or unstructured data, whatever, and you have a search space basically. And in that search space, when you want to search for a particular uh, content, then you have to go by the indexes. So if you have, say, 1 million data records, then if you do sequential implementation, you would at least need, worst case, 500,000 operation on the average. Now, what Grover's algorithm would do is it will uh, take the root n, that is, as the number of searches go by n, the size, if the search space is n, then you need actually order of on, as we said, big O notation. But in this case, we will be able to do, if you have a million search, instead of doing 500,000 operation on an average to get to the winning or the target which we are searching, we can reduce it by a root of that, whatever the size is, in this case million, so we have 1,000 operation. So essentially what we are saying is we can reduce the number of operation by a order of root n, or quadratic they call it. So we can get search done in quadratic. Now how, etc., we'll see, but we'll go through some examples to understand. So first thing is we on the speed up. So we know that there are two aspects. One is speed up, other is the complexity. The speed up is, suppose if you do each search takes 1 second, and if you got 1 million, then we'll take 1 million second. That's the order n. But in this case, we are going to do it in order of log to the n. Now log basically, because if we say n equal to 2 raised to n, then if you have example 2 raised to n, if I take first thing is a raised to x equal to n, then log of n to the base a is equal to x, which is the index. So a raised to x, so 2 raised to n. So if I have an index of n and 2 raised to n, let's say if it is 5, then I have 32. So I have a search space of 32, and I should be able to hit that according to whatever the algorithm, in this case Grover's algorithm, we should be able to hit it in 5 searches. So that's a quite an improvement. You can see 32 versus 5. That itself gives you that you can reduce the time to execute. Instead of 32t, you are doing it 5t. That is one aspect of it. The other aspect is about the complexity. Now the question is, complexity is not necessarily just in terms of time, it is also on the combinations that are there. So how do we describe the complexity besides the search? Besides the time factor. So normally what happens is there is something called in computer science we called as NP, which is what you call as, if you have a example to understand NP, I'm just giving you a simple example here. If A is true and B is false, suppose two variables, and if you take A and or B, okay, that is one, and the other if you take A, so A and or, so A and or A. So what it means is that if you have a solvable problem, then the order, first thing is complexity. Complexity is measured in terms of polynomial. We say that if it is a, or if you have a polynomial order, then you can solve it in polynomial. So one is detecting, the other is solving. You can validate that this problem can be solved. So that is the polynomial, in polynomial. But can you solve it? No, not necessary. So the problems are defined as NP, NP hard and NP. So to verify non-solvable problem, we call it as not solvable in polynomial time, we call as NP. And solvable polynomial time, we call it as P. So we verify that we are able to do in, this is for only decision logic, okay? Not for every algorithm. We are talking about decision, because here the decision is in the Grover's algorithm, we are talking about search, right? So we want to search and say, hey, this is the right index where I can get the content which I was looking for. So let's move on. I will just again show a simpler probably method which Gokhale has suggested, that if you have a pizza and if you have got different layers, so one can be a pepperoni pizza, other could be chili, pepper and bacon, and third could be olive and mushroom. So olives and mushroom. So when you have zero topping, then there is no topping at all. So we call it as one, complexity one combination. If you have one topping, then you have got either it can be none or it can be one pepperoni example in this case. If you have two toppings, then the combinations are 4. You can have no topping, or you can have, so the order keeps on increasing. If you have 8 toppings, then you can keep on doing combinations. So if you have 20 toppings, then you have got 1 million combinations. So this is the case of exponential complexity. See, order going by 2 to the power n. So as many toppings, if you have 3 toppings, then you got 2 to the power 3, which is 2 to 4 to 8. So you got 8 combination. So speed up and algorithm complexity, we have to differentiate. In this case, this is the complexity showing the complexity in terms speed we saw. So this again go back and look at algorithmic complexity we showed in Deutsch algorithm, which Gokhale had discussed, you can see there the complexity of the order was 1, because you do one computation and then say not n computation, just say one computation and then able to get out. So the order is not n but log n. Log, when you say log n, if log to the base 10, and if it is n is equal to 10, then 10 to power 10, you got 1, so the order becomes 1. So basically size does not matter, you can keep any size, but you will always be able to compute in one way, one shot, and that is what the complexity is. So for Deutsch algorithm, we can do it with 1. Now let's look at some of the other algorithms. So Deutsch, here is a comparison. Size is n, unit in which you can compute is 1. Therefore, this is a constant or a balance. That is what we saw. So big O measures O1. So this is in one shot you can get it. Linear search, if you have n entries or size is n, then you need n units. So it is called, for a linear search, like in an array or a list, if you keep doing one after the other, ultimately you will find that in 50% of the time you will be able to get it, but the order is n. Now if you do Grover search, here I am talking about a raised to n is exponential, but 2 raised to n is quadratic. So in Grover search, we say that if you have n equal to 2 raised to n, then we get a n by 2, which is n to the power 1 by 2, which is root n. So this is quadratic. So if you have 4, you can get a root 4. If you have got 100, you can get a root 100. Like for 1 million, we said that we need the root of 1 million, whatever that turns out to be. If it is 1000, it's 1000. So that's the quadratic order. There are other factorial algorithms like Shor's, which deals with the integer factoring of prime. So if you take an integer, whether an integer is, first of all, can be factored, and if it can be factored, does it result in a prime? So that's of the order of log n. Then see, when we say log, we always refer to base 10. If you say ln, then it is log to the base n, or sometimes you say log 2. Either way, here the order is log n, and we will also get into this factoring, which is important. The last one I should mention, which is very popular in the communication algorithm, is the discrete Fourier transform, inverse Fourier transform, which is nothing but take a function and split it into two parts, which are even and odd sequences, and if you apply, then you can get in 1 by n. So for the size n, you can get it by 1 by n order, and that's the speed and complexity. Now, simplest example, I'll take an intuitive to introduce Grover's algorithm. So here is a table. Here got 8 names, and I'm encoding them as A, B, C, D, E, F, G, H, and phone number associated. So in a phone book, you find that you got the name and the number. So numbers are here. But if I'm told that I have a number, let's say this number 08000555, how do I get the name as Mary Lam? So that's a different thing. Now, so you got a number and you get the name in a phone book, then you encode each of the numbers, and in this case we have 8, so we encoded with 3 qubit coding, and this is 110. And if I have a 110, that's the target, or this is the winning, you can say. And each of them have a probability of A, B, C, D, E, F, G, H is 1 by root 8, because there are 8. But when we apply the function, we get Fg, because you are taking all of them and simultaneously executing. And then if you find that you got 1 by root 8 by having that particular number, that means if you provide this input, you should be able to get this output G, which will turn out to be Mary Lam. So this is the intuitive way of looking at it for a simple search. Now, what the algorithm is right now, it's a black box to us, right? It's an oracle. We have to figure out how we get there. But before we get to the oracle, we need to know some of the important things, as how do you algorithmically present this. So here is a problem description. and you can see here F01 n minus 1. So there is a string and you are mapping n string to a 0 or a 1. That is, in this case, it is turning to be one string. So what is this fx? So either it's a 0 or a 1, and here you got 0, 1 to n minus 1. So indexes can run from 0 to n minus 1, and when we structure this on unstructured database like that, and then we get a fx, one of the uh, inputs, which turns out to be the correct input or the target. Example, we took that number, some number, and then trying to get the string associated with it. So in this case, fx is equal to 1. So fx is equal to 1 if the data that x points to x satisfies the search criterion. Obviously, if it satisfies the search criterion, then only we get a 1. Otherwise, we get 0. That's what it means. So we say fa equal to 1 and fx equal to 0 for all x not equal to a. Now, not equal to are used in different ways, but this is one of the way to present it. So this is illustrating the database with n search space, and then you are trying to have a string that is pointed out by this. So now what happens is, to simplify Grover's algorithm, because n is capital N, we just say that because you can always fill in with some entries which are um arbitrary, or which may, because you can always go uh, without loss of generality. I will say that if you have n equal to 2 raised to n, if it is not, we will try to. So example, if we have only 5 names to be searched, then still we'll be using 8, because it's more than 2 to the power 2 and less than 2 to the power 3. So essentially what we are saying is, we will always be able to generally put up a number n which is equal to 2 raised to n and fill those which are not. And we will spot that one of them, x, is the or search, which x is equal to a is what we are trying to find out. Let's say our winner, or a search which we are targeting. And if we can get that, then the other numbers we can say are 2 raised to n minus 1. Instead of saying 2 raised to n, we can say 2 raised to n minus 1. So here is the Grover's algorithm. So again, it is repeating the same things. You got 0 to n minus 1. And when fx is equal to 1, which is what rest of them are 0. So the problem is, find x such that fx is equal to 1. In this example, it is equal to a, because we were talking about the string. So important thing is, we can, if we call it a, then we can say it's a ket a. So we are trying to look for a ket a, which is the first factor. So that means for Grover's algorithm, there is a algorithm always are bunch of processes. So the step way is, we need to know that we are looking for a ket a, which is in the search space of n minus 1, and which is described as 2 to the power n. And if we drop this one, it is 2 raised to n minus 1. So out of the 2 raised to n, only one of them is the search target, and rest of them we can describe as 2 to the power n minus 1. So the first is establishing what is the vector we are looking for. Okay. Now, next one, we are looking for how many. So what happens is, there is some important thing we need to note, that a, ket a, is what we said, but there are n 2 to the power n, or let's put it caps n. So if you have got so many n size of the space or the indexes, and you are only dropping one, then 2 to the power n minus 1 is what you are left with. So if you say that a in a vector space, this is a Hilbert space, and in vector space we have got multiple qubits, then what happens is, you have each of the qubits we are representing in terms of ket A and not being ket A. So if it is not ket A, then it is one of those n minus 1, which is ket not ket. So we call it as, they are uh, in a what you call orthonormal. They are mutually exclusive. So they are. So we call it as A, ket A, and ket A T, or transpose, let's call it. You can call it A delta, A whatever, A prime, whatever you want to call it. But the product of those two, inner product of those two will be 0 because they are not the candidate. So basically we have to only find one candidate A which is orthogonal as well as orthonormal to A transpose or A transpose K. So therefore this AT is the second thing which we need to know, and this can be represented here as 1 by root 2 n minus 1 sigma x equal to 0 to 2 to the power n minus 1 of the x. So x is nothing but this x except this. So x equal to 0 for all except x equal to not equal to a. So for not equal to a, you are getting a 0. For equal to a, you are getting a 1, which you know, which is the ket A itself. So we are defining that all the other basis states are 1 to the power root of 2 n minus 1 sigma x 0 x not equal to a to 2 of this x. So this is just a definition, and this is normalization. Because you have to normalize, right? If you have got 2 raised to n minus 1, you have to normalize. So basically we are making sure that we have x specified along as a alternate to ket A, or we call it AT. So we have defined now two things. First is we have defined A, the winning candidate, and the search space other than the winning candidate, which is A transpose. And they are mathematically represented here as summation of the various vectors. And then, so now we need to define a third vector called phi. Now phi is 1, so you can see A, and this is the, so you can represent this in a what you call a circle or a square space, because A and A transpose, or A, I wouldn't call it transpose, AT, A reverse T, I don't know what to call it as, but
You can
A
call it as
and
perpendicular, a perpendicular.
A perpendicular, let's call it. So if you call A and A perpendicular, they are no, they are perpendicular to each other. Therefore, they are mutually exclusive. So their what you call the inner product is equal to uh, 0. So now what happens? If I have A parallel to A, if I do a product of that, because they are parallel, then A dot A, if I do, it will be 1. Whereas A dot A perpendicular is 0. So now our goal in algorithms, Grover's algorithm, is to have a vector called phi, which is at an angle theta to the A perpendicular, and that theta, if we can somehow uh, rotate it, and by applying some process, we should be able to bring it slowly and converge it to A, and then in that case it becomes a what you call 1, right? So that means if we are able to get to A, which is what our target is, if we can get to A, how do we get to A? By applying some kind of a rotation. So first, to apply a rotation, we define a vector called, or a vector called psi, or a basis which is a linear combination right now of the n by 2. We saw that there are 2 to the power n, right? So we know that we should be able to get it in half of it. This, like we said, million means half a million, we should be able to do it. So in this case, what we do is we take 0 to 2 to the power n minus 1, which is our overall thing, and normalize it and put the ktex. So psi is defined as a vector which is a unitary basis, a normalized vector which has an angle theta with respect to A perpendicular. Now this is the first vector, and we call this as the real uh, linear combination of the which is close to, which is very very similar to this with some angle. Now we take a rotation of that. If we take a rotation of this, the image theta, the image theta will go down. So if we apply another vector called v, because to transform a vector, because our goal is to get this phi to match with a or reach a. To reach a, we have to multiply by some, we have to, sorry, not multiply, but do a tensor operation, so that we can do a tensor operation on this to move the needle in the clockwise direction. To do that, first we take an image. If you have a phi and if you have a vector v, and if you want to rotate that vector v around phi, let's assume that it is at a image, that is, it's a mirror image type. So if you have theta, there is a theta. So we have a v of phi. If we multiply v by phi, we should be able to take an image. So we have a phi, we take an image which is v phi, which is nothing but a. So we are rotating phi around the parallel a, and which is a theta rotation. So if we define this, then we say that it has moved, the distance is now 2 theta, right? Effectively, we have rotated v by theta across the uh, what you call the a perpendicular. And if we apply another w, which is another vector, so first we apply a v to get the image, and then we say now we rotate it around this phi, which is now 2 theta. So we go 2 theta to get, we create a w, which is another vector, whereby we should be able to get 2 theta. So every time we keep creating 2 theta, 2 theta, 2 theta until we are able to get to A. So this is a geometric explanation. So what we are saying is A perpendicular and ket A perpendicular and ket A and phi are drawn in the same plane. Therefore, we are able to move this. And this is a linear combination of both um, all the n by a raised to n by 2 minus 2 raised to n minus 1 combinations. So let's take now this into a little bit more detail so that we can understand. The idea was what? To reflect phi about, so we saw the phi, and this phi we want to reflect about a perpendicular. And if we reflect, then what happens? Initially, the angle between them is phi, and if we reflect, it produces a clockwise 2 theta. So you saw that it produces clockwise 2 theta because we are reflecting this on this, so we are getting 2 theta. Once we get 2 theta, then what we do is this can be accomplished by a matrix V, which we can figure out what the matrix is. Now, if we take a matrix W, which will perform another rotation, but this time equally up, it will be in the opposite direction. That means we can find a W which will move the equivalent rotation. Instead of clockwise, it will go anti-clockwise because we are rotating this V with respect to phi. Earlier we respected phi rotated with respect to this. Now we are reflecting around phi. If we reflect around phi, we need 2 theta, so it goes 2 theta. So now we have got a WV phi which is much closer to A than what it was earlier. So this way, this can be repeated n number of times, and that's the goal. So idea is if we can keep on adding 2 thetas every time, ultimately uh, for the number of time we will rotate, that we can figure out by mathematical calculation, it will reach, because we know that there are 2 to the power n minus 1. 1 already we have taken A as the candidate, so that is gone. So 8 perpendicular is nothing but those n minus 1. So if you have an angle which is there, in this case, what is the angle? You can see the angle is this one, which is pi by 2. So pi by 2, pi radian is 180 degrees, so pi by 2 radian. So if we can divide this into pi by 2, and then every time we angle move by 2 theta, and that 2 theta is depending on theta depends on the angle we choose to start with, and that will be very small. So if n is very large, then theta and sine theta projection on sine will be theta and project on cos, we can work out what it is. So that is what our goal is next. So at the end of the thing, end of this, all this rotational transition, we want to make sure that we have something which is 100% certainty that it is what we need to target. That is the winner target, or in this case, we call it as Kete. So let's take the step. So you create a, how do you apply now? Grover's algorithm. So algorithm we have to define, right? So now the step one is creation of a phi. So phi is what, which is what we said that this is the phi. What is it? It is linear combination. So it's a linear combination of, so all we need is to just initialize the n qubit system, which we are using at ground zero state. That is all of the zero n, which 0, 1, 0, 2, 0, 3, whatever the number of qubits we are going to take, all that n qubits, we have to apply a 0 on it and then apply the Hadamard to it, so that all of these are a linear combination of these 2 to the power n minus 1 vectors and are qubits, and therefore this is described as this is as phi. So first thing is creation of phi. Once we have created the phi, next is the cos projection and the sine projection. You know that when we look at this, the x projection and the y projection. So y, this is the x projection, this is the y projection, right? So we want to make sure that we are getting those projections, and they are described as, because it is based on what we have right now, it is phi and a perpendicular. So what we are doing is we are taking phi and a perpendicular. This is the theta and this is the angle, and therefore the dot product of this and this uh, is what we are projecting. So what we can see is we are getting a dot product of these two. Sorry, the uh, phi is the angle. So projection cos theta is equal to phi, bra phi, and ket of, which is what we are getting. And this is what we have to derive. So we have to substitute in this what is phi. That is, this is the ket phi. We will have to invert it and then put a bra phi. So we can put a bra phi and the other vector. That is two vectors. We are trying to get the product here in terms of cos theta. So we can substitute the phi, get, this is bra phi, and then we can also substitute the other part, which is y part. So y is nothing but fx, and so what we have done is we have to pull out the values of phi and substitute a and phi. So you look back, what we have done is phi we have described here and a perpendicular we have described here. So this is in terms of x, a perpendicular, and this is phi in terms of what you call the linear combination. So what we are going to do is now we are trying to get the cos component of this. So we do a cos component of it, which is nothing but uh, the combination, that is um, the 5 bra phi and kit of the a perpendicular. So these are substituted, but however we have taken the second as replaced by y by x, because we know x is the input and y is the output, and we, instead of putting y equal to 0, x equal to 0 and x equal not equal to a, we have put it as y, so that we know that these are cost component can be calculated. For the this we can simplify, and ultimately it comes out to nothing but 1 by 2 raised to n by 2, this combination. You can see that root 2 n by, they divide. So what happens is ket of, this is just a multiplication. So you have got ket x and you got ket y, sorry, ket y, ket y and ket x. And when you do a multiplication of these with respect to first component, we can take these two off, because these are nothing but going to be, one of them is 0, the other one turns out to be a combination of 1, and so we end up with a equation which is this, and this equation can be simplified as root of 2 to the power n minus 1 by 2. This is a mathematical computation for cost component complex. This is a cost projection, and for the sine projection we know that if n is large, it is nothing but sine theta is equal to theta, which is what generally we do for simplification, which is nothing but 1 to the power 1 divided by 2 to the power n by 2, because we know that at the end of the day we are getting these many combination. So based on the mathematical computation of these matrices, we get into more further detail. So now what happens, since theta is small and pi by 2 minus theta, so there is a v and w, which is what we are trying to apply, and it turns out that you can substitute this theta, which is 1 to the power 2 by n by 2 here, and then pi by 2 theta, that is coming, pi by 2 theta is coming based on the so because we said that theta is small and total angle we have to cover is pi by 2, so what we do is we take it as pi by 2 by 2 theta. So what we do is we are applying pi by 2 minus theta, approximately pi by 2, and so the W operation is nothing but 5 WV operation we are talking. Since WV operation is moving it by 2 theta, we can see V and then W. So V is moving by 2 theta and then we are applying W. So what we are doing is we are trying to get this number to pi by 2 theta, and then that is equal to theta we are substituting. We know that theta is equal to 1 by 2 to the power n by 2 here, and so all the substitution leads to nothing but cancellation, and we get a pi by 4 root n, maybe pi by root 2n, 2 raised to n by 4, and at the end of it we get. So this explains why the complexity of Goer is over root n. This is based on the WV significant comparison, and this we can actually work out in a like Kronecker notation, which you use with minus 1 raised to fx. So the function fx has to be part of the v so that we can apply it. And so when you have x and then you have y equal to fx in this case. So the fx is nothing but part of the equation. And so when we have xn, we said mapping is such mapping is from f. We had seen the mapping. So we had seen the mapping as n to 1. So basically either a 0 or a 1 for, so that means 1 qubit. So you got n qubit to 1 qubit, or 2 to the power n to 1 qubit, and that is what we are trying to do here, and that's what we have got here, a Kronecker notation. So first is we created the phi, and then we have looked at a mathematical equation to get to the number, and then we are creating the vector v, which is nothing but using Kronecker notation we are supplying with the fx, because we know at the end of the day fx0 we get 0, f1 we get flip, because it is a minus 1. So minus 1 raised to, either you have a 0 or even number or a odd number. If it is odd, then we are going to get, so in this case we have got only fa and not fa. So one case we are going to get minus, which is what we need to flip. So basically the same thing again, because it's complicated, what they have done is, because the combination, you remember v keeps on, if you keep on doing v w v w w v w v w v, there is a question which is there in the exercise which I have looked at. You have to tabulate the angle from 2 theta. What is the distance between, because the distance between this and this, as the distance from these goes up, the distance from this comes down, and when it collapses almost close to a, the VW moment, so we can keep multiplying by VW and we'll reach a state when it becomes a unit. So basically this is nothing but mapping, and the mapping happens to be based on the 1 flip, the one which is when it is winner, that is when we know that A is reached, then that's when we'll get a minus flip. So if you take the probability or even amplitude, the distribution, you will find that uh, all of them are in one. If positive pointing to positive direction, one will point to negative. Then you can flip it and get it all others negative and one positive, and the one which you want, that is the answer. And that's basically a linear combination of various VW, WV, 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 etc. n number of time, depending on, it could be half a million time. It depends on the size and the root of the size, that many time. And in the case of 2 to the power n, we are getting a quadratic gain. So basically we are doing, that is the best we can get for search, quadratic. And even in the classical computation they agree that quadratic is best we can get. And uh, depending on the worst case, obviously we are talking about worst case, we are going to get that. And that is what, again, they are trying to describe in terms of i's and j's, because it is easy to form a matrix manipulation with i's and j's. So they are again describing beta as representing the vector I, which is running from 0 to 2 to the power n minus 1. And then if we do v multiplied by beta, again same thing. Here we are trying to get v I equal to 0 to n minus 1. And so this is just replacing x by I in this case here. And then we are getting the same thing, but with a uh, separation between the two. That means we are separating the ith row and one of the one which is victory, which is the target. So we have implemented here in such a way that we are able to differentiate the two. And I will say that formulation of this, anyway we will have to go through one more process. And so I will just say that at the end of the day, first is you are doing the Hadamard to get a linear combination. After Hadamard you are doing a rotation which is using the v and the w vectors. And when you do the v and the w vectors, the ultimately when you apply the w repeatedly, you end up in a alpha beta gamma. In this case they are using gamma with phi and phi t instead of phi perpendicular. Phi and phi perpendicular. Why phi and phi perpendicular? You can have a rigid rotation or you can have a, see, this is the phi and phi t. So if you keep rotating clockwise, anti-clockwise, instead of that you can rotate the frameworks. So phi you can do that way. So there are multiple ways to skin the cat. You can do it uh, either through clockwise phi rotation, or anti-clockwise clockwise, or by phi and phi t. So they are just trying to describe that using a different term in this case. And you will also find in our next lesson we will have some different terms there. But important to remember is that, say, third phase, you are, when you are applying w, uh, then the w should be able to get you two separate uh, what you call gammas, where you have a row multiplied by the column. Turns out to be you have only one value which is winner, or one value which is targeted, which is kete. So in this case it is going to be uh, application of 2 phi, because phi is what we have taken, phi and phi t. So phi t, that is nothing but mutually in the opposite direction, and you are taking a, the, to achieve this we need to apply w, and w happens to be the oracle, and that has to be 2 into ket phi bra phi minus I. Now how we arrive it is, it's there, but this is the function which is called diffusion operator. At the end of it, you are trying to get the operation to identify that winning candidate and the target, and that is using the Hadamard followed by the what do you call, the rotations, that is the transformations, and the transformation at the end of it, this has to be applied to n because it depends on the n qubit. So this is what the diffusion operator, and the derivation of that is also available to us. This is similar, since phi is equal to Hadamard n number of gates with a 0 ends. That is, this is the ground state or the initial state. We have qubits. We are initializing with Hadamard to be make a linear combination. Once you take the linear combination, we have to apply the W to it, and to W V and W to it. And so to apply the W, we have to take the kit phi and bra phi combination, which is nothing but subtracted with minus I, which is nothing but an identity. So this identity, once you apply this formula, then you can keep on variations of that. Example, here you got H. um, H we have taken, because bra version is using H. This is bra and ket. So bra version is described as a dagger of H, and then after dagger of H we can replace it by H, because H dagger and H are same. So therefore you replace it, and then I you can always multiply by I. These are all to simplify the equation. And once you take a Hadamard HH equal to I, then you can split the 4 and bring the jugularity to get the H in one place, and this is what the final equation. So why is this done? This is to simplify the implementation and uniform implementation. I think I will just stop here with the circuit which is shown to you, that you take a number of qubits equivalent to number of size, and then you, which is 2 to the n power n, then you apply the Hadamard on all of them n, and then you create the phi, which is linear combination, and then you apply a vector v to make sure that you are differentiating at least one of the targets, which is what we are looking at depending on the inputs, and then repeat this VW rotation to pi by 4 into root 10 times, which is what we calculated. So this W operator is called diffusion operator, whereas this, so you basically first you ensure that you identify the target and then you amplify it. So either you call it diffusion because it comes out of the diffusion is the photon. If you are using photon, then if you have a slit photon, a slit, then it diffuses. So that's what we are trying to implicate here, that it is diffused to a particular outcome, and that outcome is what we are getting here. So this is the end of this. The circuit is there, but we are already 12 minutes past beyond our time. I will leave the circuit to be discussed later, but this is what we are going to take as an exercise, and we have in the next session all these details. There are some links in the references here, and you can go through them. I think I should stop here. If you have any questions, please go ahead. One or two questions before we close. Anybody, any questions, please? Okay, I think this requires a little more additional exercise. So when we go through next time, we will be able to do this in a better way. Based on the timing, I have tried to explain, but grows, yeah, we will have to do at least part of it we'll have to do, and then I will stop the recording here before anybody has any question. Any questions? Okay, I will stop it and then you can ask question freely if you feel that is important.